First, a small announcement. Since the last colloquium, we joined the European Physical Society Young Minds program as an organizing committee of colloquia. So when we hold it in this way, we will get a better network and also better funding. So that's something to look forward to. It's a small announcement. Then today, for the colloquium, we will tackle a very timely topic, because you probably all are aware that in February of the current year, there was an announcement of the discovery, the first direct discovery of gravitational waves by the LIGO experiment. And this is why we invited the speaker, who is really an expert in the topic, Professor Prof. From KU Leuven. He started his career with undergraduate studies at KU Leuven. Then he did first a preparatory master year in the University of Cambridge. He also did his PhD under the supervision of Professor Stephen Hawking, with whom he still closely collaborates. Afterwards, he held postdoctoral positions in the University of California at CERN and in the University of Paris. His research is focused in quantum gravity string theory, so the tools to combine general relativity with quantum theory and the holographic principle, and he applies it to systems such as black holes, gravitational waves. So we will tackle today, so I open the floor.
Thank you for the invitation. It's nice to be here. So I'm going to talk about gravitational waves, and I'm going to let you listen to them. If you hear it. So that's the sound of, as you certainly learned from their press conference, that's the sound of two medium-sized black holes colliding, generating a burst of gravitational waves, provided you listen from 1 billion light years away. Okay? So that's an event which happened 1 billion years ago. Those gravitational waves have traveled from the site of the collision in the distant universe to Earth and have been registered by LIGO, as you've all heard 1 million times September 14 last year. So that's a little beep. That's all we hear. That's all we get. Nevertheless, I'm going to try to explain you today that there's an enormous wealth of information and potential in that little sound, provided we understand what it is, analyze it, and build a detector. So I'm not going to talk too much about that beep. I'm going to try to convey today that that beep is really one of these rare moments in physics where deep theory meets experiment. And we'll give you a flavor for what that's set in motion. So my talk is, the outline of my talk is very simple. It's theory, observation, and the future. And the bottom line will be that this beep will really go down, I think, in the history books as one of these amazing sounds that science produces. Like the first telephone or whatever, that kind of sounds. Okay, so what is the theory we're talking about? Well, it goes back to Einstein's general relativity, which he wrote down not on his blackboard, of course, but in 1950. At the time, this theory was regarded by the Nobel Prize Committee as reckless speculation. It was way off anything to do with the real world. Nevertheless, Einstein pursued for 10 years, his new theory, and he wrote that down in 1950. So what is that? What did Einstein do? Well, general relativity comes down to an entirely new way of looking at gravity. You know that Newtonian gravity speaks of a force. The force remained mysterious for centuries. Einstein said, there is no force, gravity has nothing to do with the force, it's pure geometry. So Einstein rethought the notion of gravity and said it's really what we perceive as gravity is really a manifestation of the geometry of space and time. So this G stands for geometry. It's a matrix. Mu and nu are its indices. They run from 1 to 4, time, and the 3 space I mentioned. The matrix is a solution of a set of differential equations, which are written on top there. 10 differential equations, 10 coupled differential equations. Those differential equations relate the matter content in the universe, or the matter content in your system, the energy momentum tensor, T mu, to the space-time geometry. This is a tensorial object, which is a function of G, the geometry, and its derivatives, its spatial and time derivatives. Okay? So the way general relativity works is very simple. You give me your matter or energy, and Einstein will tell you what the local geometry of space-time looks like. This is an example. You put the sun, it's a heavy mass, it's just at rest, it doesn't move very much. What will happen if you put the mass of the sun here? The geometry will be that of the usual Euclidean flat space far away from the sun, but it'll be bent a little bit in the neighborhood of the sun. A little bit, because there's this coupling constant. And this coupling constant is extremely small. It's pretty much the smallest coupling constant we know in nature. 8 pi g over c to the 4th is 10 to the minus 42. It's extremely small. This means that the geometry of space and time is extremely stiff. You need a lot of energy, a lot of matter to ever slightly deform space. In the case of the sun, the curvature of space near the surface of the sun is about 10 to the minus 6 relative to the flat Euclidean geometry. Okay? So this is minuscule, yet it's sufficient for planets like the Earth to move around in this curved geometry, because you create a sort of valley in space, and naturally planets will be orbiting around the sun. They will be kept in orbit. Also light, by the way, which was extremely confusing in Newtonian gravity, also light rays from distant stars will be bent as a consequence of the deformed geometry near the surface of the sun. So that's general relativity in a nutshell, and that's the theory which this is all about. Or the theory, or the reckless speculation, according to the Nobel Prize Committee in 1919 of Einstein in the early 20th century. By the way, this leads to extremely beautiful pictures. This bending of light near the sun has been observed around distant stars as well. That's a distant galaxy, far, far in the universe, and this ring around it is just a light from a star behind it, from a galaxy behind it, which bends around the intervening mass. So you can create beautiful pictures, and even in Hollywood they know this. The way they get us to see something of a black hole is by putting a star behind the black hole, and this is nothing but the starlight being trapped in the gravitational field around the intermediate black hole, creating these visual effects. But this Hollywood hadn't figured out. because that would also be fun for a movie. That's if you replace the sun by a black hole and the Earth goes around it and you watch it from a distance like you're doing, that would be pretty much, this is a GR, a relativity simulation of what you would see. Anyway, general relativity meant, and Einstein wasn't really ready for this, but general relativity implies a completely new picture of space and time. And all of a sudden, the fabric of space and time becomes dynamic, becomes changeable, deformed, and so forth. So and it was very clear from the beginning that relativity made a whole bunch of predictions which were just not there in Newtonian gravity. The first three followed immediately. It made the right prediction for the orbit of Mercury, so that was the first test that Einstein did, in fact, before he published his theory. The bending of light, as I discussed, that was the famous test in 1919, which made Einstein world famous. An expedition was launched to Africa to actually check this effect. The expanding universe, we won't be talking about that today. And then black holes and gravitational waves. That's the subject of today's talk. These two predictions, 4 and 5, are the most, well, together with 3, they're far-reaching, but they were also the most confusing ones in the early days. And I want to spend a moment explaining how eventually people settled on the fact that, on the theory of black holes and gravitational waves. Just to illustrate that for about 50, 60 years, with general relativity, physics was in pure theory land. This is far, far removed from any observation, and that's what makes the discovery last year so much of a milestone, okay? It's really one of the discoveries of the century, I think. Okay, so black holes go back to 1916, barely 1 month after Einstein wrote down his theory. A German soldier, Karl Schwarzschild, while at the Russian front, incidentally, found the first solution of these differential equations that I showed you earlier that describe general relativity. Evidently, he was kind of surprised to be able to find the solution, and who would he tell? Well, evidently he had to write to Einstein because no one else understood the theory at the time. So he wrote a postcard to Einstein, in which he writes, as you can see there, as you see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take his walk in the land of your ideas. Not bad for a soldier. And he ended his postcard with the actual, on which he wrote down the actual solution. The solution for the geometry, the G, the matrix G that I talked about earlier. Einstein responded, expressing his being surprised that you can actually solve that complicated set of coupled differential equations exactly, and find a solution. So the solution that Karl Schwarzschild, who died in fact a few months later, found is the following. There's the geometry G, my matrix, which we'll return over and over again in my talk. And the geometry G in general relativity defines for you a notion of physical distances in space and in time, in space-time, okay? G enters here, ds is an infinitesimal distance. If you want an extended distance, you integrate ds from A to B, okay? So once you know the geometry, you can do your physics, you're in business. Schwarzschild solved these equations, and he put on the right-hand side, the side of the energy momentum tensor, he put a heavy point mass M. It was a kind of Gedanken experiment, toy model, one single very heavy particle, so to speak. And he solved the equations, and that is the matrix G that he found. It's a diagonal matrix, so I could just write it out easily on one line there. Huh? You know that geometry If I drop this term, and if I drop that term, you all know that geometry. Yeah? I've done it here. It's just empty space, Euclidean space in spherical coordinates, and the time direction. It's the geometry of flat, empty space, the geometry of special relativity. So Schwarzschild just modifies this a little bit. The heavy mass, which he put at a value r of the radius equal to 0, modifies that geometry by this addition of term. So there's one integration constant, Rs, and Rs evidently is related to the mass. If you say, well, the mass is equal to the mass of the sun, then the value of Rs will be about 3 kilometers. That is crucial. 3 kilometers. This is way inside the sun. So Einstein thought, well, that's irrelevant. This geometry is fine, but this term will always be very, very small, because I'm far away from the sun at a radius little r, much larger than Rs, and so I don't need to worry too much about that term getting large. Huh? Nevertheless, if you want to understand that solution in its completeness, you better know what happens. What does this mean? When I go down, imagine you really have a point mass m, much smaller than 3 kilometers. What happens when you approach that point mass, and when this term, when you get to a radius r equal to Rs? At that point, this thing blows up. It becomes infinite. So in a way, and that goes to 0. In a way, time stops flowing, and it also sort of kind of takes an infinite time to get there, seemingly. Eh? So in trying to understand that solution while firing his gun, Schwarzschild became very confused, because it seemed that at that surface, at the surface he means r equal to Rs, space and time appear to become singular and appear to end. And someone else, Droste, who also found that solution a couple of months later, realized that it would take an infinite amount of time to reach that limitless radius. So that radius, Rs, was an extremely confusing radius. No, it was not clear what was happening at that surface in the early days. And that confusion continued for decades. And this is my point. It really was very difficult to come to terms with the kind of reality, the kind of view of space and time implied by general relativity. Although there was one man who did figure it out, but who never published it, at least not in English. And that man was Lemaitre, the Belgian astronomer, who wrote in 1933 that the singularity of the Schwarzschild field is a fictitious singularity, analogous to that which appears at the horizon of the center in the original form of the de Sitter universe, an expanding universe. Lemaitre realized that all that fuss at that crucial radius here, where this seems to go really bad, where space and time seem to be blowing up, is all an artifact of using bad coordinates. Coordinates t, r, theta, phi here are arbitrary labels of points in general relativity. You can change coordinates and your solution can look entirely different, even though the physics is the same. But if you use bad coordinates, you get misled. And the whole science community was misled for decades. And that's the root of Einstein's famous statement: if this result were real, it would be a true disaster. Einstein said, okay, Schwarzschild, your solution is fine, I agree with the mathematics, but physically, it's going to be completely irrelevant. And that was the position he maintained till late in his life, till the Second World War. And it's only after the Second World War that the black hole theory was finally put down, formulated, understood, and made into a rigorous framework. That's what we now know as black holes. And these are the four cornerstones of black hole theory. The Schwarzschild geometry, which I gave, describes a black hole with a radius Rs, given by the mass of the point mass. Most importantly, black holes form when heavy stars die. That's illustrated in that famous diagram, which is due to Penrose. You take a collapsing ball of matter. If you start with enough matter, meaning more matter than a few solar masses, then under its own gravity, that body of matter will continue to collapse. There's nothing to stabilize it. There's no known force in nature that is able to repel, that is able to counter the gravitational attraction. And at some point, gravitational collapse continues all the way to a kind of point mass which is not understood. But the most important thing is that when collapse proceeds beyond a certain point, there is this other surface which emerges, and that is the famous Schwarzschild surface, the R equal to Rs surface, which featured in the Schwarzschild geometry, and which defines a region of space which is out of causal contact with the rest of the universe. That's indicated by these light cones here. These are the usual light cones of special relativity, future, past, spatial distances. The light cones get tilted. And if you reach that surface, they're all the way tilted, so that everything which moves in time, which moves forward in time, is moving towards the interior, towards the collapsing star, inside the black hole. There can be absolutely no communication with the outer world. That's the physical picture which only arose 50 years after Einstein formulated his theory. It became clear, and that goes back to that paper by Lemaitre, that that surface itself, the bounding surface of the black hole, is nothing special. You could just zoom through it. You can't return, but you could just go through it. That's the third point, and the fourth point is known by John Wheeler, as a very famous physicist, involved in the Manhattan Project. In fact, he was the one who, after the Second World War, wrapped it all up, made black holes into a physical, was instrumental also in coining the term black hole, and coining the term that black holes have no hair, which means that the end state of collapse, all the way up here, is, as in the Schwarzschild geometry, uniquely specified by the mass of the object. Whatever way you start here, the final state is extremely simple. It's just a mass, and the rest is pure geometry. So those are the four things you have to remember, because that's what makes this little beep you heard the first minute a historic moment in science. Right? That little beep tests it all four of them, and much more in fact. Now you might say, well, did we not know anything about black holes before September 2015? Well, the answer is no, of course. Everyone kind of thought that black holes effectively exist. And we have sort of pictures of black hole, active black holes. This is a picture of Centaurus where the black hole is surrounded outside that special radius with a huge matter disk, in fact, which then, through the interaction between gravity and electromagnetism, creates this spectacular phenomena. Also in the center of our galaxy, we do probably have a black hole. But what did astronomers mean when they say there's a black hole? Before September 14 in 2015. What do they mean? They mean there's a heavy mass in a fairly small area. But fairly small was still meant way larger than that magic RS surface. Electromagnetic astronomy, traditional astronomy, was not probing that special surface which was at the heart of the black hole theory. It was probing a much larger area, because nothing can remain near the black hole. It would just fall into the black hole. So there are very few information through the electromagnetic radiation that we have from black hole regions. So that's when we come to the second theory pillar of the whole game here, gravitational waves. Gravitational waves is a completely different medium, has nothing to do with electromagnetic radiation, and that's the crucial point. It allows us to probe the universe in a completely different way. So what is the theory of gravitational waves? It also goes back to Einstein's general relativity. In fact, it was Einstein himself this time who first deduced the existence of gravitational waves by analogy with electromagnetic waves. In fact, Einstein was conceptually driven by the analogy with Maxwell theory while trying to formulate his theory. So it became an immediate question for him. Does there exist an analogy with the electromagnetic field? And so in 1916, he finds that. But he ends this paper in a dramatic way, because he realized, because of that small coupling constant, that gravitational waves will never have anything to do with physics. Unobservably small, irrelevant. And, well, you know Einstein, he can sort of then formulate this in the most dramatic terms that you might imagine. Eh? Then in 1918, Einstein changed his mind. In 1922, Eddington, famous astronomer, says, well, these gravitational waves, they move at the speed of thought. They come and go. Einstein couldn't decide whether they were real or not, because he was again confused about coordinates and so forth. And even as late as 1936, Einstein and Rosen published a paper saying gravitational waves do not exist. And upon submitting this paper to Physical Review, which at the time was a very good journal, they get the reply from the editor. There it is. No, this is not a reply of the editor. They get a reply from the editor saying that they're not going to publish their paper because the referee said that the paper is wrong. And this is Einstein's reply to the editor of Physical Review, saying that he had sent them their manuscript for publication, not to send it to some referee who would disagree with it. And so then he decides to publish elsewhere, he says, and in fact he adds a PS to his letter, saying, Mr. Rosen, his collaborator, who has left for the Soviet Union, has authorized me to represent him in this matter. And this is the paper in which Einstein and Rosen claimed to prove that gravitational waves do not exist in 1936. Why was that? Their reasoning was, well, gravitational waves are an approximate solution of general relativity. You linearize this complicated set of differential equations, and then you solve it. And Einstein and Rosen had a kind of argument that this linear solution could never be a solution to the full theory. That the non-linearities of the full theory would sort of conspire to make these solutions away, so spurious solutions. Right? That was the crux of their paper. The referee, incidentally, was a colleague of Einstein at Princeton. Good. So the story of gravitational waves, the theory, is sort of analogous to black holes. A lot of confusion about coordinates and the way the physics was to be extracted from the theory and so forth. And just like black holes, only in the 60s a consensus arises that gravitational waves indeed existing. By that time, they had understood how to get rid of all the spurious imaginary gauge solutions and got into the real physical waves. They're really waves. You start with Einstein's theory, you look for an approximate solution where this is the geometry of flat space, special relativity, Minkowski space, and this is a small perturbation. You solve for the perturbation. What you find is that that perturbation obeys really just a wave equation. So a solution to that equation is a gravitational wave. This is an example of a gravitational wave, and the argument here is Ct minus z means the gravitational wave is moving in the z direction. It has an amplitude A, and then there's, because this is a matrix, your coefficients are matrix coefficients as well. And the general solution is not much more complicated, and here is gravitational wave theory. The gravitational waves propagate at the speed of light. They're transverse, just like electromagnetic waves. You see, for this wave in the z direction, only the x and y directions, spatial directions, are perturbed. This is the time row, the x row, the y row, and here is the z row. So there's no perturbation in the z. The geometry in the z direction is just as if it was empty space, flat space. So they're transverse, just like electromagnetic fields. They have two polarizations, cross and y, and they carry energy. So those are all features which flow out of general relativity, and yeah, which were tested last year. Huh? Now, how do you get gravitational waves? On the one hand, it's simple. Everything which moves will, via the Einstein equations, make space-time vibrate. The bad news is that all sources of gravitational waves are staggeringly weak because of these extremely small coupling constants. So to generate appreciable gravitational waves, you need large masses of the order of the mass of the sun or even larger, and you've got to speed them up very fast to the order of the speed of light. Those are the kind of systems you're interested in. So an example, the example which featured in the LIGO press conference, are two black holes or two neutron stars in very close orbit with each other. That will generate a significant quadrupole, and it's the quadrupole moment which really gets you going, which really generates gravitational waves. But the quadrupole moment is multiplied again by this very small coupling constant. So a significant quadrupole moment can get you to a geometry perturbation of order 10 to the minus 21. Extremely small, on the one hand, but an enormous amount of energy on the other hand. In that small geometry perturbation lies an amount of energy which is way beyond everything else in the universe taken together. Taken together, okay? This is larger than all the light of all the stars and all the galaxies taken together. So we are, with those gravitational waves, probing a kind of realm of the physics of the universe, which is way off our grid so far. So that's very promising, but that's an enormous experimental challenge. How do you get going? The last thing that I need to explain you in order to understand the experiment is what gravitational waves actually do. If a gravitational wave passes the Earth, what happens? Well, I've been talking about geometry. A gravitational wave, the geometry G. A gravitational wave is a fluctuation of the geometry of space. So what can it do? There's only one thing it can do. It can't interact. It can't collide. It can't do anything but changing the physical distance. the geometry, as I said, defines the physical distance. If I'm going to vibrate the geometry, I'm going to oscillate the physical distance between different objects. And that has indeed been the trick that the LIGO experiment has exploited. So this is a little more technical, but it's crucial to understand the experiment. Consider two particles separated a certain distance L star in the x direction. And now, say there's a gravitational wave passing, it's transverse, so let it pass perpendicular to the two particles. Then the distance between these two particles is given by the geometry in the x direction. So the geometry in the x direction would be 1 plus the perturbation h. That perturbation h, if it's a gravitational wave, is that sine function, is oscillating. And so the fractional change in the distance between these two particles over their distance, if you work it out, is just oscillating with the gravitational wave. That's the key point, right? But here is again their amplitude. This is again or 10 to the minus 21. So that's the experimental challenge. So if you do the same thing with a ring, that's what you get. Eh? You take a ring of particles and you let the gravitational wave passing perpendicular to the ring, it's going to stretch and shrink in two different ways, corresponding to the two different polarizations of the gravitational wave. Good. Observation. In fact, even the observational front has its history. As early as the 60s, Joe Weber was going around the world claiming he had seen gravitational waves with his famous aluminium tank, which he had filled with detectors. And so he had in mind that when a gravitational wave passes, the signal would be transferred to an electromagnetic signal by his detectors. So many labs started to try to reproduce Weber's experiment, but no one got ever anywhere. But he continued to claim detections till he died a couple of years ago. But the experiment that really set the scene for LIGO, for what you heard about last year, was this one. This is the famous binary pulsar experiment, which consists of two neutron stars in very close orbit with each other. So there's a significant quadrupole moment. So they generate gravitational waves. But one of these neutron stars is a pulsar, which means it's an extremely accurate clock. It sends out a beam. And the beam, every fraction of a second, passes through Earth. So you can very accurately determine when one orbit is over. And notably, Taylor and Hulse have observed such a binary pulsar system for years, literally years and years and years. And they have observed, because the arrival time of that pulsar jet and the orbit, they have observed that these two neutron stars came closer and closer and closer to each other, gradually, very, very slowly. And that's what you see here, expressed in terms of seconds, starting from 0. So this is the number of seconds that the orbit shrinks. And on the vertical axis, years. So they've observed this system for years and years, and gradually the red dots show that the two neutron stars approach each other, ever so slightly. But the blue curve is the prediction of general relativity of the energy that this system emits in gravitational waves. So Taylor and Hulse had not seen those gravitational waves, but the fact that that prediction of general relativity agreed so well with their data is what the National Science Foundation in the US finally convinced that they were going to support and build LIGO. So this is the famous indirect evidence for gravitational waves. And it's the same kind of system that LIGO was interested in, not two neutron stars, but imagine even better, two black holes colliding. You wouldn't see any electromagnetic radiation, but there would be a burst of gravitational waves emitted at a collision, which travels through the universe, through the stars, through everything. It doesn't interact because the coupling constant is small. It travels through Earth, makes the Earth wiggle, and it's those wiggles, those distance changes, which LIGO was after and which they claimed to have detected. Why that shape? Now we understand why that shape. If a gravitational wave passes, in fact the gravitational wave they observed came from the other side of the Earth, passing through the Earth towards the States, you need that kind of rectangular structure, precisely because if one arm shrinks, the other one will stretch. And you want to play these two effects against each other. So the way they set up the experiment then was to build two such detectors. One in Louisiana and the other one in the state of Washington. Two identical rectangular structures, each arm 4 kilometers long. And inside these arms, the whole game was to monitor the distance between mirrors inside these arms. This is an illustration. Yeah. There we go. So they have a laser. They make the laser beam split and bounce off a mirror. And they set, effectively, they set a trap for the gravitational wave. They monitor the distance in that direction and in that direction, and if the distance is equal, nothing moves. But when a gravitational wave passes, the position of those freely floating mirrors will change ever so slightly, and when the distance is, and that will produce a signal at a detector. That's the experimental setup. It's really, the best way to think of this is, it's a trap. It's a trap for a gravitational wave, and this is the man, this is the guy, Ray Weiss, who actually had the idea back in the 70s. But evidently the experimental challenge was huge, because none of the parts of the experiments, the technology existed for nothing. They could start, everything had to be developed. And the biggest challenge they had in the end was to, evidently, was to keep these mirrors in place. So they run an easy version of their system to hang these mirrors from in the early parts, the early years of this century, which did not detect anything. And then they heavily invested in a system, a very sophisticated system to hang this mirror from, which goes in 4 steps. And at each step, the thing vibrates. And you know, if you vibrate your pendulum very fast, your mirror will just stay put, right? And so they have 4 levels of vibrations, all connected into a single glass structure, which doesn't absorb the photons of the lasers which are hitting the mirror, to keep those mirrors exactly in place. And so those mirrors have to be, in general relativity terms, freely floating. Freely floating means not, moving, only sensitive to changes in the geometry of space. That's what freely floating means. So that was the challenge, getting these 4 mirrors perfectly in place. So that's a picture of this system. And okay, when that was all done, that was what I started with. Evidently, the key point about sort of experimental confidence in this whole game was that you saw the same thing in Louisiana and in Washington. That's kind of the obvious experimental check here. In fact, you saw the same thing with a few nanoseconds difference, which is the distance, which is the time it takes for the gravitational wave to travel from Washington to Louisiana. Speed of light. So there's an enormous constraint on the fact that gravitational waves effectively travel at the speed of light, thanks to this single direct observation. So that is essentially the signal. That's a visualization. So what did they see? That's the paper, but this is where it all comes together. Okay, let's now bring this observation and the theory that I explained all together, and then this is the key slide, key graph where this is done. Okay, so what did they observe a signal? So they start from a signal. The very first thing they did was to filter out the high frequency noise, because that's all detector noise. They knew this. Okay, so they filtered this out, and they get a much smoother signal, which is the gray band here. And you see that the signal, the frequency increases and the amplitude increases, and then it suddenly dies out. You would not know to do anything with this signal if you didn't know general relativity. But after 100 years, and after these 50 years of confusion which I sketched for you, the general relativity community was ready to interpret this signal. And that's the red curve. The red curve is a prediction, a solution for the matrix H mu nu that is obtained from general relativity, starting with two black holes which both are lightly spinning, their spins are parallel, and they're in bound orbit together, and eventually their horizons will extend a little bit, they give their final kiss, so to speak, and they form one big black hole. That is a system which has a quadrupole moment, and then it stabilizes into one big black hole. While it has a quadrupole moment, the system will emit gravitational waves. You put that system on a heavy computer, and the red curve is what comes out. And so that is the real success of this, the real historic moment last year. The thing, as you can see, matches extremely well. Now, you're used to discoveries in particle physics, they discover new particles, new resonance, all very fine. But this is not just a resonance, right? This is not just a number, a mass like the mass of the Higgs particle. This is an entire curve. It's an infinite amount of data in a way. You can read off a lot of information because every deviation in your system is going to have an effect on this curve. So why did they wait 4 months before announcing their result? Well, they have a huge library of general relativity systems, like these two black holes. They had to find the right one, evidently. If they make the black holes bigger, then this peak will go up, and the frequency will stretch. And so every little change in this system will have an effect on the prediction of the curve. So to interpret the data, which is what they started from, of course, they had to find the right system that, according to general relativity, predicts this curve. And so then, once they have this is the list of predictions that comes out. That's the signal of two black holes. Hence, there is no electromagnetic radiation at all involved in this business. Evidently, we're talking about gravitational waves. The initial masses of the two black holes involved were fairly large, 30 solar masses. The total amount of energy that is radiated in this process is about 3 solar masses. But bear in mind that curve here We are talking about a fraction of a second. So that's why there's so much energy in it. A fraction of a second, 3 solar masses disappear in gravitational waves. There's an upper bound to this radiation. That's part of black hole theory. The square of the masses of the initial black holes has to be less than the square of the mass of the final black hole. It's one of the most profound results in black hole theory to do with the link between relativity and thermodynamics and all that from the 60s. And indeed, this is verified here. The square of those masses is less than the final mass was about 57 black holes. You can deduce the final mass from the way this decays. You see sort of an exponentially dying amplitude here. That exponentially dying amplitude is perfectly calculable in general relativity and gives you the mass of the final black hole. As far as we can see, there's agreement with general relativity. It's the first test of relativity when gravity is strong. And it also tells us, evidently, about a new kind of system in the universe, a pair of 2 black holes. Evidently, with electromagnetic astronomy, we hadn't seen a pair of black holes before. So that is really very rare in physics, that so many different aspects of a theory all come together in a single experiment. What's the time?
It's 5.
How many minutes? Good, well, that is just the kind of simulation one has to do. So they were lucky, by the way. I told you that the final system that matched the data was a pair of 2 black holes with parallel spins. Imagine they had been spinning like this. It would have taken 8 months to run the computers and predict the data. It's bizarre, it's miraculous in a way that today, 100 years after general relativity, we are just about capable of solving these 10 horrible coupled partial differential equations to make actually the predictions and to test our theory. Yeah? This is one slide that I included specifically for the experimentalists in the audience. That's the kind of more systematic way of looking at this whole game. 0pm means Newtonian gravity. That's a way of parametrizing gravity, general relativity, as corrections to Newtonian physics. Just for one parameter, one specific parameter. The blue things were previous experiments in the solar system and all that. So there were the bounds on this particular correction to Newtonian gravity given to us by general relativity. The yellow squares is what comes out of this single experiment, the gravitational waves detected by LIGO. So this single experiment shows us that we are already constraining general relativity way better than all the previous experiments ever done. That's what is the core of this, what is happening here. Gravitational wave astronomy is literally a whole different ballgame as far as general relativity is concerned, and therefore as far as the physics of black holes and so forth is concerned than we had before. So pictorially, the way I see this is that via these gravitational waves, we really have a new link in physics. We link a realm of theory to a new kind of astronomy. And the future is bright, eh? Every time we have opened a new window onto the universe, This has led to surprises, this has led to breakthroughs, this has led to profound changes, ultimately also in theory. And with time, I believe, we're going to have the same here. Eh? So, very, very quickly, how does the future gravitational wave astronomy look like? Well, one thing is to continue what's been going on with LIGO here on Earth right now. So we have these two detectors here in Hanford and Livingston. Those guys are operational. GEO is operational, but less sensitive, so they didn't see anything in September. But Virgo and Gagra are both coming online very soon. And even the Indians are now on board to finally proceed with the construction of their detector. And all these different detectors, they work together. Just as Hanford and Livingston were working together in this detection, when a gravitational wave passes, we're all going to see it. It's the same gravitational wave after all. And so they work together, and the big advantage is going to be that with all these detectors, they're going to be able to pinpoint where these sources are. Because right now, there's a big area in the sky where these two black holes that they saw colliding might be located. They don't know this very precisely. But with that whole network of detectors operational, that's going to be possible. Second direction for the future is, of course, to go into space. Europe has plans, and the plans are looking better and better every day, to launch a kind of gravitational wave detector in space, which will be trailing the Earth. 3 satellites you see there, and they're connected by laser beams, again, to monitor the distance between the satellites. It's all we need to do to detect gravitational waves. Monitor very carefully the distance between satellites. So each satellite, deep in the interior, will hold a gold clump of 1 gram, held in perfect free motion, meaning only sensitive to the geometry of space. Deep inside each of those satellites will be an identical gold clump, and then there will be a whole infrastructure around it to measure the distance between these 3 gold clumps. Why do we need to go to space? Why can't we do the same thing on Earth? It's the same as in electromagnetic astronomy. The answer is the same. It's the frequency. The distance between those satellites will be 1,000,000 kilometers. That's impractical to do on Earth. Therefore, that experiment will be sensitive to gravitational waves with a much longer wavelength. Gravitational waves with a much longer wavelength are generated by a whole class of different objects. Objects which are much larger. What object can be much larger than a stellar mass black hole? These are the supermassive black holes in the centers of galaxies. Those are black holes of masses of 10 to the 6, 10 to the 7 solar masses. They're huge black holes. So when 2 galaxies collide, you have a similar setup. These 2 supermassive black holes in the center of both galaxies will exhibit a similar kind of orbital motion and ultimately merge. Those mergers are involving even bigger energies emitted in gravitational waves, and are by far the most energetic events in the universe, by orders of magnitude. If you can observe those mergers, which is a prime observable for that experiment, you can essentially trace back our history, the history of our universe, using those mergers all the way to high redshift. So you can sort of gradually reconstruct in a way the wave structures, the way galaxies formed in our universe. So that's a kind of cosmological analog of the gravitational wave experiments on Earth, which are primarily focused on stellar black holes inside our own galaxy. So that's the same thing here. Here's the frequency. Low frequency up in space, high frequency down on Earth. Low frequency, we have the massive black holes, the galaxies, we have other possible tests of general relativity and possible deviations, and here high frequency, these are the neutron stars, and the black holes. But it's even better than this. There are some systems which we can observe at low frequency whilst they're orbiting each other. These stellar black holes that LIGO is talking about, that were observed, when they're far away from each other, months before they're gonna collide, we can observe them up in space. Then they leave the frequency band of sensitive to the space experiment, but a few months later, the final fraction of a second of the same system, they will be sensitive on Earth, and then they will collide. So if you can combine those two experiments, so that's like literally what people do in electromagnetic astronomy, in the usual astronomy, all the time now, then you're really into business. So this is just to illustrate that this is a brand new branch of astronomy that is about to get going. The last point is cosmology. Cosmology in a very early universe, evidently this was also a big change of game, involves also gravitational waves, and is yet another probe of, with gravitational waves of new physics. But so that's what you heard about a couple of years ago via the microwave background radiation, subtle polarization signals in the microwave background radiation might reveal also something about primordial gravitational waves emitted essentially at the Big Bang. So this is the whole spectrum, the whole game. On Earth, high frequency, inside our galaxy, neutron stars, stellar black holes. Up in space, huge black holes involving collisions of galaxies. Cosmology, these are gravitational waves with a wavelength, essentially the order of the observable universe, huge wavelengths. And in between, I haven't talked about that, there are other ideas to get information about gravitational waves as well from careful pulsar timing experiments. You can ask me about that if you're interested. So that's essentially my conclusion here. We have a new era for precision testing of general relativity with these gravitational waves. And it's especially the future which is, I think, extremely interesting and promising, because it's just a new way of looking at the universe. It's a way of looking at the dark universe. And if you know that only 5% of the matter in our universe is visible matter, it looks like there's a lot to discover. And gravitational waves are one way to go in that. So cosmological structure formation from these space experiments, precision tests, cosmological experiments about the very early universe. And ultimately, I think that these gravitational waves, as it's always the case in physics, ultimately gravitational wave observations will probably mean the end of general relativity. Will probably signal subtle deviations of general relativity, and therefore set us on track for a more complete theory of gravity, which is quantum gravity. So, thank you.
Fascinating observation, fantastical. What convinces me most is that we have a coincident observation of these two parameters. It's probably very improbable to have a signal in both in this very tiny window is being considered. But I have another question about probability. Before we had this observation, what did we expect? What the frequency of this kind of occurrences? Because I understand the events were observed even before the data taking of the space started. They were doing some test runs and immediately they saw this event. So that makes one think that these kind of things are very frequent or occur very frequently. Is that also what was expected, or did we expect to see them once in 100 years? Or
yeah. Okay. So first of all, yes, these two detectors have to see the same thing, otherwise they don't even consider it a valid thing. As far as the frequency of those systems, the bets were off by a wide margin, going from 0.01 per year to 400 per year. The reason for that enormous range is simply that we can't see black holes. We just don't know. We really don't know a lot about that 95% of dark matter. The bets were mainly based on the systems we can see, pairs of neutron stars, like these pulsars. Neutron stars, many of them are pulsars, and so people had some statistics about those. And it was really an extrapolation. You make the neutron stars heavier and heavier, you will turn them into black holes. But the uncertainties are there because of uncertainties in structure formation models. That's why the astronomers are so excited by this business, because now they get data about what for them was the dark universe.
But there are other rumors that they see more?
Oh yeah, no, yeah, sure. Yeah, I was with Ray Wise in Harvard just 2 weeks ago. It's clear they've seen more. Yeah. In fact, they waited before publishing until they had seen more in order to convince themselves that there was nothing wrong with this engineering run. There was one piece of their experiment, I forget what it was. Nothing with the detectors themselves, but something with the data analysis, which wasn't working during the engineering run. And so they waited until they had seen more events. I think there will be another press conference in 2 weeks. Yeah.
A question on the same lines. So this is about.
Loud and clear, please.
Okay, sorry. I have a very similar question about the probability of these events.
Yeah.
So, just asked about the events that have been observed, which are, say, order of magnitude stellar mass black holes merging. You mentioned at the end of your talk that future experiments will be looking at the centers of galaxies colliding. So how frequent are those expected to be?
They're very infrequent, no worries, they're very infrequent today. But the point is that when two supermassive black holes in the center of galaxies collide, it's a huge signal. It's of a sensitivity of 1,000 above the noise. So you can see those guys way back in the distant universe, 10 billion years back. Well, then galaxy collisions were frequent. In fact, that's the way big galaxies formed, by merging smaller galaxies. So the whole, sorry?
And the whole signal takes a lot longer probably. Observation can be seen much longer in advance.
Yes, I think it's a matter of maybe days or a few days for these collisions. It's a matter of the frequency band again. When the merger is, it's out of. There's another, I didn't even talk about that. It's beyond our lifetime. You could build an even bigger experiment and then you would see them longer. The reason of the uncertainty, theoretical uncertainty, is that structure formation in the universe is easy when the fluctuations are small in a very early universe. It's a linearized theory. But when the fluctuations become of order 1 and you really form stars and galaxies and so forth, it's a mess. Not that much is known about the details of how stars and galaxies together formed and this and that. That's the uncertainty theory. Well, here you have your experiment to inform.
I'm curious about how this can teach us more about quantum, because you can only see very bright events. It could be like trying to figure out the properties of a single photon, but all you can see is the brightest lamp in the room. Like
That's not a bad analogy. Here's the trick. I didn't explain. Well, one is cosmology, so primordial gravitational waves from inflation, teach us something about the underlying quantum fluctuations that give rise to inflation. But stick to black hole physics for now. Then this is your man. These guys, extreme mass ratio in spirals. That's what's given here. Here you have your geometry of a supermassive black hole in the center of a galaxy. Here you have a little black hole, a stellar mass black hole, orbiting that supermassive black hole. With this experiment up in space, that orbit can be followed for months, literally months. Now, if you follow an orbit in general relativity for months and months and months, you have an extremely precise determination of the geometry G, my matrix G. If that G near the black hole deviates just a little bit from what Schwarzschild told us, you have it. That's the idea. Small deviations of GR. And the reason I mentioned it is that in recent years, in theoretical high energy physics, it has become clear on conceptual grounds that general relativity is not going to break down just in the deep interior of black holes, where you have a singularity. Okay, obviously it's going to break down there, that's like the Big Bang. But it must, for conceptual reasons, break down on a scale larger than that. The only other scale in the game is the horizon scale, which is this RS. So there are theoretical arguments that you should see some deviation of general relativity. No, that's the wrong way. That there must be some modification of general relativity on the scale of the horizon. Now, whether it is accessible to us in these kind of observations remains to be seen. I don't know. I really don't know. But that's the state of the art.
If you want to triangulate the position of let's say, the couple of super black holes that collide together with these all detectors all around Earth, will the two events arrive at the same time? So the light from those events and then the gravitational wave?
No, not necessarily. That's a very good question. Sometimes yes, sometimes no. For instance, the famous example are the supernova explosions, where if a heavy star rotates and undergoes a supernova explosion, its core collapses and can form a black hole. That collapse, if it rotates, will have a quadrupole moment, and therefore will emit gravitational waves. The gravitational waves, thanks to the small coupling, will just propagate at the speed of light right from the star. But the photons will have to go through the whole structure, the whole collapsing structure, and will bump into each other and so forth, and will be delayed. So you have to then coordinate. You have to understand the physics in order to sort of identify.
It's going to be feasible.
Feasible. Yeah, I think so. So the main point is that they need all their detectors. No, so okay, the way this works is they have a deal. They have a deal with 60 electromagnetic usual astronomers. Okay, whenever they have an event, LIGO, that triggers those 60 collaborators in the electromagnetic astronomy community to look in a certain direction. Now they can't tell them where to look because they have this big patch of the sky. Okay, so they're stuck. They did trigger them, but the astronomers said, okay. But if they have 5 detectors and the gravitational waves arrive within a nanosecond from each other in all these 5 detectors, then they pretty much immediately, for the very good events, have a spot in the sky. Because the orientation is different of those 5 detectors. then you can work with the electromagnetic community. Incidentally, in between the photons and the gravitons sit some other observable, right? The neutrinos. And so in the case of the neutrinos should arrive only a fraction of a second after the gravitons, after the gravitational waves. So in an ideal world, you have the guys at the South Pole alert this.
I have a couple of comments instead of a question, and you have to tell me whether you agree with it.
All right, cool.
So, we are clearly living in the decade of some spectacular fundamental discoveries of experimental verification of fundamental science. It has demonstrated that the incubation time, first of all for the theories to be socially accepted and mature, about a decade.
At least. Yeah.
The experimentalists need to prepare their proposals for another decade, and then they need to construct experiments for 20 years. So that's how you arrive at 50 years time before you detect this phenomenon, right? What we've shown with this discovery, also with the discovery of the Higgs particle and so on, is that we are now able to confirm our most fundamental theories of nature. We are at the technological level where we can close these theories. And we should be ready now, perhaps with this generation or with the next generation of experiments, to start to observe the first deviations from this, which will have truly fundamental impact on physics.
Yes, because this we knew already.
Yeah. Will our society will need to make choices in which fundamental discovery they want to invest next?
And it's going to be a lot harder because politicians need to know that you're going to find something like the Higgs or like gravitational waves, and what if we have to tell them, well, we might find nothing? Or we don't know what we're looking for, which is the case now, right? Yeah, but maybe we can discuss this afterwards. No, but you're right. I think this is the key. So it's a society question. I agree. We will need the support of the society at large and a sort of spirit, a long-term discovery spirit, to keep moving. And up till now, we had exquisitely detailed theories like the standard model of particle physics and relativity. The current generation of experiments, neutrino experiments, LHC, and those kind of gravity wave experiments, if we're lucky, will point towards something beyond. If that's not the case, you're gonna have to be really taking a course in science communication to keep going, right?
Do we know whether or not these gravitational waves exhibit the normal wave behavior? So can a gravitational wave experience diffraction around a larger gravitational well? And can we then, with detecting those gravitational waves, find out information about the gravitation, about the structure of these gravitational wells? Or
structure of these gravitational?
No, the real question is, can these gravitational waves exhibit the normal wave behavior, like diffraction? By example, around another gravitational well.
Yes, okay. Around the gravitational well, yes. But then you need a gravitational well of an enormous magnitude. So in practice, for any of the foreseeable future, those gravitational waves, once they're emitted in a complicated process involving a gravitational well, they're freely propagating waves with two polarizations moving at the speed of light. That's been verified, but other than that, very few information. They're freely moving waves. Yeah.
In the case of this observation, you had 3 solar masses that were radiated
Yes.
in gravitational waves. Now, what made it to be 3? That's my first question. And then the second question is, if it's supermassive black holes, how will they predict what kind of radiation we will see? What is the magnitude?
With supermassive black holes,
Yeah.
it's exactly the same system. You put these two supermassive black holes on a computer and you run your simulation. That is, you solve these 10 differential equations numerically. So why is it that this is so difficult? You need to do this for all sorts of masses of these two black holes, all sorts of spins, all sorts of relative positions of the spins, and all sorts of angles of the plane of motion with respect to our observing infrastructure, right? So they now have a library of about 10,000 templates, as they call it, and they match these, they try to match these with the data. But you're asking for an intuitive explanation, why 3 solar masses? I don't know.
I guess it also comes out of this complex system, right? That
Exactly.
Yeah.
This is a little bit of
It's a combination
difficulty.
of all the parameters of
Yes.
the force.
Yes, there's a range of masses.
Yeah.
You can't go too large because of Hawking's area theorem that says that the surface area of the final black hole must be larger than the sum of the
Yeah.
surface areas of the initial black holes. Meaning that the mass squared of the final black hole must be larger than the sum of the initial mass squared. So all the 1,000 string theorists in the world, what did they do when they saw the press conference? They did the back of the envelope calculation to check Hawking's theorem. Because the sum of the masses evidently is small, because it radiates away. But the 3, I have no intuition about it, in this case. Yeah.
But that is what fits with the observation.
Right, it goes, yeah, I've seen a lot of those templates. It goes from 0.1 solar mass up to pretty much the maximum. You get the maximum, so, yeah, that may be another, okay, that's maybe, okay, maybe this goes some way towards your answer. You get the maximum emission in gravitational waves up to Hawking's bound when the black holes are rapidly spinning. There's a maximum spin that a black hole can have. And those are the systems which emit the most. Those black holes that fit those data were hardly spinning initially. So that could sort of explain that you're way below the maximum. Yes?
You say that they ran simulations for 4 months with different settings of the parameters to find the right combination. Is this like a 100% certainty, or is there still some other chance that another combination of parameters might give the same?
This relates to your question. No, it's not 100% certain. They don't have the exact. It's a phase space kind of thing, right? You try to fill the phase space of possible configurations with predictions that you have, but this is what comes closest. This is what they have now. And in fact, they have 2 categories of simulations. One in which they can simplify the system to an effectively one-body system. Those are the cases in which the spins of the initial black holes are parallel. Then there's a complicated order transformation you can do to simplify the system. Those you can do in a matter of days, those simulations. And then they have the complicated configurations in which the spins are not parallel and the black holes are rotating and all that. That's a single system, takes a couple of months. So they don't have the phase space of the actual system. They were lucky because in their simple library, which they have, they found already a system which fitted the data. That's the whole story.
Okay, thank you. We're going to close the questions. Let's take a speaker here.